Hello, my name is Dr. Wang. I'm a professor from Department of Chemical and Biomolecular Engineering from University of Tennessee. And today I'd like to talk to you a little bit about the confidence interval in statistical ideas as to what the heck is confidence interval, when would you want to use it, what does it get you, how do you incorporate in a report, and I'll also give you a couple examples in another video. So right now I want to talk about confidence interval, CI acronym. Exactly what is confidence interval? Well, it has the following form, as you can see in these two formulas. And don't worry about memorizing formula. This is in every standard undergraduate textbook. Mainly, I wanted you to understand what this formula says and how do you interpret the result using this formula. So what is a confidence interval? Confidence interval gives you estimation of the actual population statistical value you really want to know, but you can't afford. You want to know the entire lifetime of all the bulbs you ever produce, millions and millions of a particular company. You can go out and measure. All you can do is go out and sample, say, 25 light bulbs selectively. You get a sample mean, which is indicated by X bar. All the bar and the X mean sample something. All the Roman numerals, or is it Greek, mus, refer to population mean. The entire population mean, which is what you really want to know, but you never have the luxury of knowing. All you can do is sample, get the bar value. So what you want to be able to say is, I don't know what the population mean is if I were to go out, sample everybody, but I can tell you with, say, 95% confidence, it lies somewhere between a lower bound value and the upper bound value with 95% confidence, based on only limited sampling. And this interval of uncertainty is called the confidence interval for instance, sample mean. Population mean. This is population difference of two population means. You will improve your process, either before and after lifetime of your bulb. This improved process, you want to compare. Indeed, you go out and sample the entire population has to improve. So you construct an interval for it. And most probably, the industry prefers 95% confidence. You can do a 90%, 100%, 99%, but most of the people will do 95%. So we'll be concerned with 95%. And in order to construct a table, we will need two tables, the normal distribution table and the t-table. But how do you know when to use a normal distribution table? Remember this magic number. This magic number, happiness is finding the sample size is larger than 30. If you have larger 30, you use the z-table. What's the z-table? This is called the normal distribution Gaussian table. If n is less than 30, you got to use the t, student t distribution table. By the way, why student t? There's a little anecdote. An English statistician worked for a beer company back in, 18th century. So did some result about distribution of sample mean and so on. Found out it followed a certain distribution, mathematical distribution. He couldn't publish it because it's under contract, so he submitted as a student. And so it's called student t distribution. Anyway, I'll show you a couple examples later on how to differentiate. Just remember 30 is a breakpoint. Okay, so the form is, I don't know what the true mean is, but I can tell you it lies between x bar minus something and x bar plus something. What is this plus something? That's uncertainty based on, you can see x bar and what is s? S is the sample standard deviation. You have, say, 15 samples, you collect all the values, you calculate a sample mean, you calculate a sample standard deviation. I'll leave it to you to find out how to do that. Again, it's in every statistic book. N is a number of sample points. So with this, we can travel. So what does this mean? So this means then, again, we have a confidence interval over here that you calculate. This is that x bar minus is whatever the uncertainty is. This is x bar plus is uncertainty. Uncertainty, this thing right here. This is the uncertainty. This is that delta business right here, if you're doing difference. Anyway, we say, I don't know what the true mean is, but it's somewhere here. Somewhere, I can tell you with 95% confidence, for instance, the true mean you're really interested in is somewhere in here. So if this interval is narrow enough to be acceptable by your whatever application, EPA, you're cleaning up some river, you say, hey, I don't know where, all the point along the river, if you were to do, I don't know what it is, but I know the contaminant level now is between here and here. If that's acceptable by EPA, you go with it. If it's not, then you better do an additional cleaning up effort or lifetime of whatever you produce. So this is called the confidence interval with the lower bound and the upper bound. And at whatever, say 95%, you know your mu is somewhere in here. So how do we construct this? That formula shows you what it is. It's your sample bar, sample mean. Okay, now let's talk about what governs the size of this uncertainty business. Suppose it's a 2y, you need to bring it down. What do? You notice this uncertainty here. Let's just go ahead, write this down here. Again, let's see what that is, all right? So this is sample standard deviation. Okay, this is the delta business. Let's look at this. Well, as we can appreciate just intuitively, the more samples you actually, the more sample points you take, the truer your x bar is going to represent your true mean, mu. But is 12 or 15 enough? No, I would say not. So we know the bigger n is, the smaller this delta is. So it's got to be an inverse relationship. As you can see from this formula right here, n appears in the denominator. However, it's not just a simple 1 over n. It's 1 over square root of n. Why square root? This has to go into theory part, which I'm not ready to discuss, but just take my word. It's a square root. What does this mean? This means you want to bring the delta size to half. Say this is too big. You got to increase n by 4 times. Square root of 4 is 2. 1 over 2 is half. So if you increase to 9 times, square root of 9 is 3, then you reduce to a 1/3. So if your management, if your boss, she says, hey, this is too wide, I can't accept this, then you say, okay, the only thing is I got to increase the sample size. Well, why don't you increase the sample size to begin with? Let's save you all the trouble. We are all engineers, and what is our concern? I mean, if you make for manufacturing, of course, I work for university, yeah, money is still a concern. What we are interested in manufacturing is money, money, money. That's the bottom line. So if you increase the n, more sample points, more money, more time, more ado, more processing, that all means more money. So they, a lot of times, don't want to allocate a lot of money for it. But if they give you too large an interval, what do? You've got to increase the n. Okay, now let's look at this comparison difference of two means. You claim you improved the process. I improved the lifetime longevity of some manufactured components. The car engine, for instance, lasts longer now. Oh yeah, let's go ahead and do a sample. You do an N1 sample point before your improvement, N2, you get an X1 bar for before, X2 bar after, S1, S2. Let's go and construct interval. So the interval you can construct then is going to be something like this again. This is X1 bar minus X2 bar minus something. X1 bar minus X2 bar plus something. You say, okay, this is mu1 minus, I don't know where the true difference is, but I can tell you with 95% somewhere in here. Here's the most important idea. You want to improve something. You want to increase the lifetime of an engine. You want X2 to be bigger. Let's say X1 is after, X2 is before. So you want the X1 minus 2 to be a longer time. So you want to make sure this is a positive number. You want to make sure this is a positive, this entire thing is a positive number. So that means I don't know what the actual improvement, the longevity is. I can tell you it improved by between this number, how many days, months, years, or miles, and this number. Now, so you want both positive. Say this is 2.5 years. And this is 4.2 years. So this is the engine part, let's just say. Both are positive. Then you can say, yes, my improved process did increase the longevity of a part. However, if this is 0.6 years, say, and this is 5 years, let's just say that this is your interval for mu1 minus mu2. You say, hey, this looks pretty good, 5 years. Can you actually claim my improved process increased on longevity of the engine? Hell no. Don't you dare to put on your report, because if you do, I'm sorry, if I be your management, I probably find a cause to fire you. Look at this negative number. What does that mean? That means there is a certain probability, you just don't know, that your improved process actually decreased the longevity. Because it straddles the 0 point. Straddles 0. What does that mean? It means 0, meaning no improvement. It also can be this. You say, but look, Dr. Wang, this is just a tad, minus 0.6. This is a whole lot, all of 5 years. Can I just say I have an improvement? No, you may not, because it doesn't mean that mu, the true mu is in the middle. It doesn't mean that at all. It just means somewhere in there with 95% confidence. You don't know where. It could be minus 0.5. It could be minus 0.1. You don't know that. So if this is 0, scrap the whole test. Start again. Increase sample size until both numbers are positive. This is the most often pitfall that young or inexperienced or people who haven't had my lecture will commit in that. They will say, oh yeah, see here, 5 years, I improved the problem. No, you must construct the confidence interval, make sure both ends are positive when you're doing the difference of two true means. So I will stop here. The next video, I'll give you a couple examples to show you how I actually construct this. Wait, I forgot to show you two things. I want to show you how to more or less understand the Z table and the T table. Remember, these tables give us the numbers we will need in order to put into the confidence interval formula. So let's go look at the T table first. All right, it's just in every standard book. So when we talk about 95% confidence, then the missing area is 5%, 1 minus 95%. So when you look in T table, you see the little red area over there. So what we want to look for, for instance, a t-value that leaves 5% area under the curve to the right, which is a little red area, or 2.5% of the area to the right. And again, that's a red area. So in this particular instance, or in the two examples I'll be giving in the next video, the 5%, 2.5% refer to the area to the right. What we'll be looking for is that particular z-value or t-value that leaves, say, 5% to the right. How do we know whether to use the t-value table or the z? Remember this n equal to 30. When your sample size is larger than 30 or maybe equal to 30, that's all debatable. You use a z table, you can get away with that. The t-table distribution approaches the z as n gets bigger. So n larger than 30, use a z table, which does not care what's the sample size. When it's less than 30, especially in the teens, 12, 15, you had better use the t-table, which is more conservative. The t-table then cares about so-called degree of freedom, which is the sample point n minus 1 in the single population. But whatever it is, the 5% 2.5 refer to that. Let's take a look at the z-table. Okay, here's the z-table. The z-table does not worry about, oh, hold on, let's go back to the t-table. I forgot to show you one thing. You see the first column there, nu, which is the degree of freedom. So you find that, say your n is 15, then you look for nu equal to 14. Then you go across, look for the t-value that leaves you whatever percent area to the right. Okay, now let's go to the z-table. In the z-table, you're dealing with a bigger population. You don't care what the sample size is. You do care, for instance, the z-value that leaves 2.5% to the right. So what you want to do in the actual body of the table is the actual value. So you look for 0.025. Then you look across. The first column gives you the first digit, 2 digits of the z-value. Say look under 1.9. Then you look across the row to the top, says 6. So 1.96, I know it's a z-value that leaves you 2.5% or 0.025 area to the right. This table does not have a little picture to show you the area, but the 2.55 always refer to the right. That's why I showed you the t-table, the little red area. So in the actual numerical example, I'll be using detailed information to show you how to find those values that we want.